also adding this little question mark. Oof. Got it. I'm adding this little question mark. So if you have any questions at the end of each slide, I'm just going to have this question mark popping up, and feel free to interrupt me when this question mark is on the screen. So just, yeah, quickly, who am I and why am I talking about computer vision for satellite imagery? Daniel already kind of introduced me, but I was doing my master's degree at ETH, working on computer vision for these little guys here. They're essentially robots, kind of like the Boston Dynamic one, and I was working on computer vision for that robot. I'm also very interested in space and how space can help on Earth. So I was looking at how you can use computer vision and combine that with space. And that's what brought me to the atmospheric chemistry modeling group, where I was working on detecting methane plumes. And yeah, as Daniel mentioned, now I'm working at AWS as a solutions architect, which is essentially a sales engineer role, just with a fancy name. So before I kick this off, I just have a quick quiz to kind of test the knowledge of your general knowledge on all these deep learning things. So if you want to scan this code and put a little thumbs up so I can know you're online. All right, I think that's everyone. So first question, tough one. All right, okay. Okay, so this guy's Yann LeCun. He's the guy who invented convolutional neural networks. So yeah, just a quick question. Second one about transformers. If I say transformers, I mentioned that word before. Do you know what I'm talking about, or is this completely new to you? All right, so a bit of both. And last question, have you heard or used Hugging Face before? All right. Okay, great. That's nice. Gives me, where are you all? Oh, right here. Cool. Now we can get into it. So I was talking about computer vision to detect plumes. But if you follow Daniel's work a bit in the last few years, you know that there are already methods to detect plumes specifically for multispectral satellite imagery. So why do we need to develop some new methods or some different methods for this plume detection problem? Well, in one sentence, I lifted this off of Danielle Jacobs' review paper. And what he mentions is that it would be desirable to quantify these methane plumes from a single overpass. And that's kind of the crux of why I want to work on computer vision for methane plumes. There's two challenges. The first one is processing time, and the second one is the false positive rate. So if we talk about processing time, just going to take a quick example. So I took all the GHG RP reporting facilities for oil and gas facilities, and specifically with methane emissions over the United States, and looked at how many facilities we had, what was the volume of data for this use case, and thought, okay, if we want to develop a systematic monitoring of these reporting facilities for methane plumes, how long would it take to process all that data using the MBMP method, so multi-band, multi-pass? And so it's that method. I won't talk about that too much right now, but essentially this method is going to take two observations of a same scene and try to find the differences between essentially bands 12 and 11 in these two scenes. And it's going to try to highlight the difference, and ideally it highlights the methane plume like you can see here. the issue here is that you have to select a reference scene, and then you have to do this computation of MBMP. And that takes a bit of time, especially the reference scene selection. And if you're going to apply that to these 2,000 facilities, it's going to be about a day, of computation time per week, assuming we have one observation per week. So a day should be fine, but remember, this is just the US. And if you want to try to survey other areas in the world, then you're rapidly going into well, a lot of computation. And the question is, maybe can we reduce this processing time? And so when I tried with a UNet I developed, so a computer vision algorithm that I developed to try to detect plumes, the inference time, the throughput for one image was about 0.1 second. This is, of course, on a GPU, whereas for MBMP, it's a CPU-based calculation. So the comparison here isn't really fair. But if you're going to deploy these, that's how they're going to run. So we can see here that using computer vision, you can really drag the processing time down, which is interesting if you want to monitor these facilities systematically. Any questions on that first? All right. So moving on, second issue we run into is the false positive rate. The MBMP method works really well with a homogeneous background because it's essentially averaging differences compared to, it's looking at differences compared to the average. And when you're going to have heterogeneous backgrounds like the Permian Basin, there's a lot of clutter there. There's roads. You can see in this kind of segmentation or very amateurish segmentation map. There's some roads. There's some different topographic background. There's some water bodies. There's some well pads. There's a lot of noise there, and that's going to introduce the false positive rate. Introduce some false positives, because if you think about this multi-band multipass method, you're assuming that the difference between the two scenes that you're looking at is going to be methane. And so most likely the two scenes are going to have some slight differences that aren't methane, and that's going to lead to these false positives. So the more artifacts you have in the background, the more likely you are to have false positives. And this is why you get these results depending on the background. So this is in Algeria, where the methane enhancements are really precise. And in the Permian Basin, it starts to be a bit off because of all the clutter you have in the background. So in a very scientific wording, essentially, MBMP for heterogeneous is kind of meh, but for homogeneous background, it works really well. So that's a second motivation on trying to go for computer vision algorithms, which will only work with a single pass, and that removes some of these issues. Again, any questions here? Okay, so onto units. So I saw a lot of you choose Anderson Cooper instead of Yann Lequin. I'm still assuming you know a thing or two about convolutional neural networks. So UNet is a form of convolutional neural networks with an encoder-decoder structure. They're very lightweight for deep learning networks, and they've really been the state of the art since 2015 for image segmentation. And that's in a field that moves really quickly. So it's pretty impressive that they've managed to survive that long. So during my master thesis, I was training this UNet to try to detect methane plumes from Sentinel-2 satellite imagery. And I won't spend too much time on the architecture of UNets, but essentially the results I got, so this is on simulated data, so it's real Sentinel-2 scenes in which I embedded synthetic methane plumes. And you can see that it finds some of these plumes, some of them aren't really visible in bands 12 and 11. So I was using this metric called NDMI, which our WashU participants might know better than the others. It's normalized difference methane index, which looks at the normalized difference between bands 12 and 11, which are the methane sensitive bands in Sentinel-2. And so this UNet architecture was working pretty well. But when I went to the real world, to real plumes, there were still some limitations, and essentially it wasn't performing as well in terms of number of plumes detected. It wasn't performing as well as the MBMP method. So there's still a lot to improve if we're going to use computer vision to systematically monitor methane emitting facilities. And this is where transformers can be interesting, because the thing with UNets, it's more traditional deep learning, those convolutional neural networks. And what you're doing is training a small-ish network to perform a very specialized task. And for every new task, you're going to train a new network. But yeah, for every new task, you're going to train this new network while having to keep costs in check. Training a deep learning network is expensive, and if you want to keep these costs in check, well, it can't be too big. So I take this analogy of robots here. It's kind of like on a factory line where you're going to have different robots. Every robot is going to be very specialized for one task, and UNets, you can kind of see them like that, or traditional deep learning, convolutional neural networks. You can kind of see them as these very specialized robots. You're going to train them for a very specialized task. And that's where you have this kind of philosophical difference between the CNNs and this new architecture that's gaining traction in the world of deep learning, which is transformers. This is not a transformer. This is just a Boston Dynamic robot. But this is kind of the philosophical difference. This Boston Dynamic robot, it's pretty generalist. It knows how to do a lot of things, and then you're gonna train it some very specialized task. If it's gonna go in that same factory to try to put cars together, it's gonna be able to put in some screws, put in some bolts, maybe even paint the car. Whereas you're gonna need several very specialized robots of these orange robots to do that. So it's kind of that difference if we take this robot metaphor. With transformers, you're going to train a very large network on performing a seemingly useless task. So for example, if you think about this robot, maybe how to fight against gravity. This robot's going to learn how to fight against gravity, and then you're going to teach it how to put in a screw. Well, your transformer, you're going to teach it how to understand images in general, and then you're going to fine-tune it for a specific task. And that fine-tuning is kind of the model that makes it really widespread. You can have these big labs like OpenAI, like Anthropic, and all these AI labs training these very costly deep learning networks. Then they can open source them, and other users can decide how they use them and train them on their very specialized task. So this is just the intuition, like the difference of why we're using one or the other. Now, if we get a bit technical, I'm not going to get too technical here, but if we get a bit more technical, how do convolutional neural networks work? I found this really fancy GIF, or GIF, however you want to say it, that illustrates how this convolutional operation works. Essentially what you're doing, you're looking at one pixel and getting the context from the neighboring pixels. So you have some form of contextual understanding, but it's very localized. And with transformers, you introduce a mechanism that's called attention. It's from a 2016 paper called "Attention is All You Need." They're very funny, those deep learning researchers. And what attention does is it allows the model to focus or pay attention only to the relevant information and relationships, whether that be text or image. Here I'm talking about image because this is kind of the topic, but transformers also work with text. And in practice, what it's going to do, attention is calculating a score that's indicating the similarity or relevance between each sub-element of your picture. So if you take this picture of a dog, it's looking at the similarity between the ear or the patch around the ear of the dog and other patches in the image. And it's going to relate pretty well to, for example, this paw right here, and pretty poorly to this patch of flowers right here. And so the model is going to know that when it's considering these pixels, then it should focus its attention on this region of the image and not the flowers. And so what you're doing here essentially is capturing some form of long-range dependency instead of the more localized context of the convolutional neural networks, because here you're looking at the whole image in relationship to this area, to this patch. So another cool thing about transformers is that they can deal with different input resolutions and image shapes. That's because instead of dividing an image in pixels, you're dividing it into patches. And so if your image is 256 by 256 or 2000 by 20, if you're into that sort of image, then it's going to know how to deal with both shapes because it's just breaking it into subpatches. Whereas for convolutional neural networks, all the images that you're inputting into your network have to be the same shape. And that's going to be really interesting when it comes to satellite imagery. So I'll come back to that later. Any questions on this? Feel free.
I have one.
Yeah.
Okay, so you're saying that transformers are able to capture some more long range information and images, but in the sort of traditional CNN framework, aren't you also able to do that through through the shrinking of the image, from like block to block?
Yeah, definitely. I mean, so that shrinking of the image is what, I mean, if you go back to the UNet architecture, that's exactly what you're doing with these skip connections. You're bringing this broader contextual understanding to a finer localized context. So that's something that you're still doing with UNets, but in the end, a convolutional operation is still only going to be that patch of pixels. And with these transformer networks, you really have that attention mechanism, which is kind of that push broom going over the whole image. And so this broader contextual understanding is embedded in the formula itself. Whereas for CNNs, you're still losing some of that information as you go into more coarser and coarser resolutions. So okay. You do get that with CNN, and that's one reason why they work so well. But for transformers, it's essentially on another level, the contextual understanding that you can get from an image. So onto one of the limits of transformers is that you need way more data than the normal convolutional neural networks. They're learning a complex relationship. They usually have more parameters, so they're more data hungry. The intuition is just if you're learning something complex, you're going to need to have it repeated several times before you really grasp it. I'm not going to repeat that, thankfully. And the convolutional neural networks are going to learn simpler relationships. That means they can learn meaningful representations from surprisingly small data sets. If you take UNets can learn some useful things with 100 or so images. And if we come back to the problem of methane plumes, where we don't have a lot of data, those larger networks are really good. And that's also one reason why we shouldn't throw away convolutional neural networks just yet. But what this kind of larger network means is that sure, you need more data, but you're also learning deeper relationships. And so you can learn more information before you start overfitting to a given data set. And so that's also one reason why they're starting to perform better than convolutional neural networks for computer vision. Now, one fundamental thing about these models, I mentioned they're really large models, they're expensive to train. And so you have this difference between, you have this concept of foundation models and then fine tuning. Yeah, you're going to have some very large networks that are trained on huge data sets. That's when you hear the entire internet by companies or labs that have access to supercomputers and that can train these models. So they're going to pre-train it. So training the model on a task that can seem useless, but nothing specific to how you want to use the model in the end. So for example, for images, you're going to mask a part of the image and train the model to rebuild that image. So it seems like it's a pretty useless thing to train a model to do. But what you're really doing here is learning not just a task, but how the data looks like and what an image should look like. And once this large model is trained on this seemingly useless task, then you just have to fine tune it as a downstream user. And this is where you're going to teach it a specific task and not just understanding the data. And this is where the real advantage of these is it's that it already knows what your data looks like. And so this is something you don't have to train. So fine tuning, it's an hour or so for these super large models. And so you get to do much more powerful applications with much less GPU time, at least on your side. So yeah, maybe just an intuition on fine tuning. For example, if you want to learn how to skateboard as a 20, 30 something year old, you're not going to have to learn how to deal with gravity. You already know how to do that. You've been doing that for these 20, 30 years or so. And with fine tuning, that's the exact same thing. You already know a lot about the data. You just need to learn what the task is. So if you want to detect dogs or flowers or planes, that's the only thing you have to learn. Now, the issue with foundation models is that, first of all, is there a question maybe on foundation models? Okay, so that's where Hugging Face comes in. I was talking about Hugging Face before. There's a lot of models out there. I can just put a few images of models on Hugging Face, which is kind of like GitHub, but for these transformer models. There's close to 500,000 models, but most of them are for text and image. And one thing these deep learning models are, even though they can be fine-tuned for a variety of tasks, they're sensitive to the data modes they're trained on, which makes sense. So you're going to train them on text, on image, on audio, on point clouds, or on multispectral satellite imagery, for example. But if this model was pre-trained on text, then you're not going to be able to use it for your computer vision task, which makes sense. And the issue with computer vision models is that most of them are trained on RGB images, but not on multispectral satellite imagery. There hasn't been a lot of models for this. And so the Earth observation community has really been lacking a foundation model for its application. Because you need a large actor that has access to a lot of GPUs, that has the willingness to do it and to open source it for other researchers to use it downstream. And this is where an IBM and NASA team published this foundation model for geospatial data a month or two ago, 2 months ago, pre-training it on Sentinel-2 and Landsat data. This is HLS, the harmonized Landsat and Sentinel-2 data. And it's a combination, it's a data product that's a combination of both. And they open source that, which opens, of course, a lot of options for the Earth observation community. So the way they trained it, as you can see here, is that they masked parts of the image, encoded this, and then tried to reconstruct the image. So what the encoder is capturing here is the deep representation of the data, and then the decoder is trying to reconstruct it. So the encoder here is essentially a very fancy image embedder. And if you're going to cut the decoder off, then you have only that fancy encoder. And then we can fine tune for the task that we have in mind. So that task can be binary classification, if that's your thing, regression, if you want to quantify something, or it can be a segmentation head if you want to find methane plumes in an image. And that's where, well, it gets exciting for methane plume detection, because this opens opens the field to using these really powerful foundation models for detecting plumes. And they actually provide an example so this is burn scar detection. And well, as you can see from this example, it looks a lot like methane plume detection. They're using the same bands, so RGB and the shortwave infrared bands that are sensitive to methane to find these burn scars. And so it should work with methane. I'm trying to get it to work at the moment. But this definitely, yeah, is an exciting development for computer vision applied to methane plume detection. I mean, that's something that you notice when you look at methane plume detection. A lot of the papers that are coming out on this are using UNets, which have been around for a long time. And there's been some shifts in technology in deep learning, but the methane plume community hasn't yet been able to apply these technology shifts because of there not being any foundation models out there. And so that's where it's really exciting. I made a quick demo on how to use Hugging Face and what it looks like. I see that we don't have a lot of time left, so maybe I can take some questions if you have any before I show the demo. It's pre-recorded, so.
You can just show the demo, and then we can do questions at the end.
I hope you can hear. All right, so welcome to the demo part of this presentation. So before we jump into the foundation model for, so just to clarify before I continue the demo, so this is not specifically applied to atmospheric chemistry, but it's to motivate and try to show you how easy it is in the end to use Hugging Face and use the models that are there if you want to use them for your downstream applications. Geospatial data. I'll just quickly present this Hugging Face platform. So Hugging Face is kind of like GitHub, but for AI models. So for people to share models, data sets, also host spaces, which are a place where you can demo your models. And then there's some Python libraries for you to develop and fine-tune foundation models directly in your Python environments. So this is what a model card looks like on Hugging Face. There's a lot of models on this platform, and some of them have richer model cards like this one because, well, a lot of people use them. Others, as we're going to see later, don't have as rich of a model card. What's really impressive here, what I just want to show quickly before we move on, is this use in transformers button. So they have a Python library that's called transformers. And instead of manually downloading a model, storing it on your local computer, etc., you can just import it in your cache using these 3 lines of code, where you're going to use their transformers library to import a model. So as I said, this integration is for those models that are used a lot. So yeah, 500,000 downloads last month. The issue with our geospatial foundation model is that not a lot of people are using it, unfortunately. So we're going to have to do this fine-tuning ourselves by downloading the model to our computer. With this, you can go to File and Version and download this .pt file, which stands for PyTorch. And as you can see from its size, that's probably the deep learning model. So once you download it, you can go on with fine-tuning it, but let's first go try to see how it's trained. So for this, they provide a little demo in the spaces where you can see how the training is done. So the training is where they're gonna have this encoder-decoder structure, and they're gonna mask out parts of the image, encode it, and then try to decode it so that it looks like the original image. And as you can see, well, it does look like the image is fake at some points with these kind of harsh lines, but pretty impressive performances. And once you've trained it on a really large data set, you can chop off the decoder, as we saw in the slides, and add your own fine-tuning task. And they also provide a few demos for that. The first one is this multi-temporal crop classification. So from a satellite image, trying to see if a crop is going to be corn, if it's going to be a wetland, if it's going to be soybeans, etc. And here we can see that you're getting already pretty reasonable performances for a model that was trained on a completely different task and then that you only fine-tune for about an hour on a new task, and which is already performing pretty well. Now, important to note also is that the training and this fine-tuning right here were done with a data set called HLS, which stands for Harmonized Landsat Sentinel-2. And it's a combination of Landsat and Sentinel-2 data, and both are at 30-meter resolution. Now, more interesting to us, I mean, we're not in a lab working on crop classification, right? We're supposed to work on atmospheric chemistry. They also fine-tune a model to find burn scars in satellite imagery. And so you can see here, the forest was burnt and the model was trained to detect that burn scar. And what is really promising here is that this really looks like the methane plume detection task that we had. So it shows us that with this foundation model, we could eventually fine-tune it to detect methane plumes in Sentinel-2 imagery. And one thing that's really nice also with these transformer models is, as I mentioned in the slides, they're agnostic to the pixel resolution. So here I said that this was a 30-meter pixel resolution, but they also provide a fine-tuning task where they're working with 20-meter resolution. This is only Sentinel-2 data. They fine-tuned it to detect floods. So here again, we see 3 widely different applications. And with this 20-meter resolution, they're still fine-tuning it to try to find the water in the satellite image. So once again, some really impressive features that just make this foundation model really promising for our task of finding methane plumes in Sentinel-2 satellite imagery. So, all right. So just wanted to show you a bit those demos on different tasks and with different data. I hope this motivates you to try to use it, to try to use Hugging Face if you're looking at any similar computer vision problems. Yeah, I think it's very promising that we now have a foundational model for geospatial data, and yeah, I'm trying to spend some free time on fine-tuning it for methane, so I'll try to keep you updated on whether it works or not for this application.